is the last day of this summer school, and so today the first lecture will given by Marc about this G-2 issue. So let's welcome Marc.
Okay, so good morning. So just to recall what we have been doing, so these lectures are about two-photon physics, and what I try to give you a taste of are some recent developments at the precision frontier of hadron and particle physics, where hadronic physics is the limiting factor in order to interpret experiments as a sign for new physics. And so we have seen in the first lecture basically the so-called proton radius puzzle, which is a near 8 sigma discrepancy between the value of proton size extracted from a muonic hydrogen atom compared to electron scattering. And so we have seen there that the dominant hadronic corrections were two-photon box diagrams, which could be calculated relatively reliable. They do contribute sizably. They don't resolve the discrepancy at present, but still one has seen that the understanding of these hadronic corrections is crucial in order to interpret such data. And in the second lecture, I came back to experiments in electron scattering at larger momentum transfer, where about 10 years ago one has found sizable differences between extractions of nucleon structure quantities, such as form factors, between unpolarized and polarization measurements. And also these point to large corrections due to two photons. And I've shown you the ongoing state in this field. What I would like to do today is to look also at two-photon process, but from a different point of view, namely the fusion of two photons into hadrons. And we will see that they are basically the dominant hadronic uncertainties to the anomalous magnetic moment of the muon. So there is another connection with a test of standard model and a search for physics beyond the standard model. So let me just start from very basic things and motivate this search. So the magnetic moment of a charged particle, so in general, so we know that a particle which has a spin, so in general, will have some magnetic moment, as we know, and this magnetic moment is basically proportional to this spin, and this proportionality is the charge divided by 2 times the mass of this particle, which is the Bohr magneton. Now we know in quantum mechanics, so this was found in the first part of the last century, that this proportionality is not 1, but this proportionality involves a factor which is called the gyromagnetic factor, and experimentally this was found for the electron the first time with high precision to be around 2, and it was the Dirac theory, so relativistic quantum mechanics, which naturally explained this G factor equal to 2. So basically the precession of a magnetic moment in a magnetic field, so will be proportional, the frequency of this precession will be proportional to this, so in this way one can make such an accurate measurement of this G factor. Now, of course, the question is, 2, that's only the leading calculation, so how to understand this magnetic moment more precisely, so this has inspired quite some people. So I don't know if you recognize here, this is actually Pauli, and this is Bohr, looking at the spinning top. So one can ask oneself the question, how is this G factor predicted in the theory beyond the Dirac theory? And so its so-called anomalous part, which I will use all the way today, is the deviation of this G factor from 2, and conventionally one normalizes it, divides it by 2, and this is called A mu, so it's the anomalous part of this G factor. And so all of you who have taken first quantum field theory course, so it's basically one of the first type of calculations in such a course. If you have a vertex diagram, for instance here an electron or a muon coupling to a photon, the first correction, quantum loop correction, is coming from this exchange here of one virtual photon across the lepton line. And this was calculated first time in the 1940s, end of 1940s by Schwinger. And so he found these results that this anomalous part to this leading order, which means one photon exchange here, so with 2 times the electromagnetic coupling, so that's why there is alpha here. And this number is typically something like 1 per mil. So this anomalous part of this, so the deviation from 2 is something like 1 per mil. Now, so this has been, of course, confirmed experimentally, but not only that it has been confirmed, one has gone a whole step further. And actually, this is very impressive. So this is the most accurate calculation of any quantity in quantum field theory, which was actually completed last 2 years ago by now. So this is I think the only calculation which has been done up to 5 loops. So it's very impressive. So Kinoshita-san and his group, they've done this 5-loop calculation, and it took them about 10 years. So they have done, of course, different classes of diagrams, but 10 years to go from the 4th order to the 5th order. So there are about 12,000 diagrams involved. So this is here one diagram, but now try to imagine all the diagrams with 5 loops. So this is this quantity here. Nowadays, it's conventional to write this anomalous part in this units 10 to the minus 10. So you see there is this huge number here, but if you multiply with 10 to the minus 10, this was this 0.00116, which we saw in the previous. So this was here the leading term, and now you see all the digits which are coming here. So, and the precision, which is shown here, is at the level, so it's basically 0.001, so 10 to the minus 10, so it's at the 10 to the minus 12 level precise, this QED calculation. So it's really very impressive, so this kind of precision. Now, of course, in the standard model, so we don't only have QED, which we can calculate to very high accuracy, but there is also weak interaction. So, for instance, if you exchange a Z boson there, or you have other weak interaction processes. Now, because you have very massive gauge bosons there, so they acquire mass, as we know. So you do the spontaneous breaking of the gauge symmetry. So this weak interaction contribution will be much, much smaller. And you see immediately, so this is here at the level 10 to the minus 3, the leading term. So this is at the level 10 to the minus 9. So it's 1 million times smaller than the QED contribution. And it's known also to the roughly 10 to the minus 11 precision. So now, if we look at the strong interaction contribution, so I will show you how this is calculated later on, but I'll first show you the result. First of all, yeah, it's much larger. It's than this weak interaction, of course. So it's of the order here 7, 10 to the minus 8. So it's still way smaller than the QED one, about 4 orders of magnitude. So this is 10 to the minus 3, and this is roughly 10 to the minus 7. So, but what is important here is the uncertainty is completely dominating the standard model result. So here the uncertainty is 1 10 to the minus 12, here 1 10 to the minus 11, and here 5 10 to the minus 10. So if we measure this quantity very precisely, we will be completely swamped by the uncertainty from the strong interaction. And so one of the main challenges for theory is how can we improve on this number in order to improve on the comparison with an experiment. So yeah, these hadronic uncertainties, they completely dominate the accuracy of the standard model result. And if we look now at comparison with data, so theory versus experiment, so what is shown here, first of all, this is the difference between the theory value and the experimental value. And the most precise experimental value is an experiment which was performed at Brookhaven. And this experiment is shown here, the uncertainty of the experiment is shown here by the blue band. So basically, so this is by definition because it's subtracted, centered around 0. And then you see the band is the uncertainty of the experiment. So typically, the uncertainty of the experiment right now is 6 10 to the minus 10, which gives the width of this band. And then, so you see different theory calculations. So, and the difference between the theory calculation is completely driven by the QCD input. So the QED and the weak interaction, of course, is all the same in all these theories. But for the strong interaction, it depends which data input one is using. So I will show you how this is calculated. But if one takes the average of all these theory estimates, one sees that there's a difference between theory and experiment, or experiment and theory, which is here 26 in these units, so the experimental error is the 6.3, and the theory error, just remember from the previous slide, basically completely dominated by the hadronic uncertainty, so this 5. So the theory uncertainty is right now of the order of the experimental uncertainty, and if you take the square of these errors, you add them in quadrature, you will see this gives roughly like 8, and then, so the deviation is 26. So depending which center of value you use, you get a 3 to 4 sigma deviation from the standard model. So this is one of the few quantities where one sees a persistent clear deviation from the standard model. Of course, the proton radius, which I showed you before, is a very stark discrepancy, but it might have some other reason. It might not point to new physics. We don't know. But this seems, this has been interpreted in a relatively natural way as science for new physics. So of course, in order to really pin it down more accurately, you would like to make this more significant, and you would like to test it, so maybe there is still some error somewhere. And in order to get it more significant, one would like, of course, to bring down the experimental number, but also the theory number. So now the experimental number will be brought down. So one of the top priorities in particle physics in the US, so there was a recent priority plan, so this year, which was pointed out, is a muon facility at Fermilab, and part of this new muon facility is a new experiment for the G-2 on the muon, and this will knock down this error from 6.3 to 1.6. So it's a factor 4 improvement, and actually I just overlaid here, this is a projection of course, in red. So this will be the precision of the new experiment which will be done at Fermilab. So this will be done in about 2 to 3 years from now. So they are actually even ahead of schedule. So as I understand, so there was a recent workshop in the US organized by the spokesperson of that experiment in July, and so they have shown that they moved the whole magnet. Maybe some of you have seen these pictures. It was a quite impressive move. So from Brookhaven all the way along the US East Coast and up the Mississippi River and to Fermilab through canal systems. So it's a huge magnet, and this will be installed or is being installed actually right now at Fermilab in order to do these experiments. So the reason why they will be able to really improve on this precision, or one of the main reasons, is that you have higher muon energies available at Fermilab compared to what they had at Brookhaven. So if this would go down to 1.6 and theory would stay, then you would typically get, people estimated, you will get like a 7-8 sigma effect if the center value stays roughly the same. But of course, one would like to make it more significant, and there is no much point to improve the experimental error if you cannot improve the theory in a significant way. So a factor 4 improvement in the experimental area spurs also factor 4 improvement in the theory. So now if one will arrive there, that's an open question, but I will try to argue here, and the consensus in this field is that one should at least do a factor 2 in theory. So to bring it down to something like 2.5, which then will add in quadrature with this error 1 and 1.6.
Mark?
Yes?
For the theoretical error, did you just cite the smallest or the latest active error bar?
Yes, this is this error here. You mean?
Yeah.
Yes, I will now show you it's basically the hadronic physics input. So this is the latest numbers. Yeah.
Right. You said just taken from the latest calculation.
Yes. Mm-hmm. So let's look indeed at this QCD, or strong contributions to this G-2 of the muon. They basically fall in two groups. So strong contributions from strong interactions which are not calculable within perturbative QCD. So we have seen if we have a quantity with a large scale, we can of course do quite precise calculations, but here we have a muon which has zero energy basically, so which means that if you have such a loop, all the degrees of freedom can flow there, and so they will be dominated mostly by the low energy degrees of freedom. So the so-called hadronic vacuum polarization is by far the largest hadronic contribution. So it's basically this one photon diagram, so which Schwinger calculated, but calculating the hadronic component of a photon. So it's the hadronic vacuum polarization. So if you have the photon propagated, you can insert here a loop. In the perturbative calculation, this would just be a quark anti-quark loop. But then, of course, you can dress it with all kinds of gluons, and if you project it on hadrons, so this will be here the production of all possible intermediate hadronic states. So the leading one will be like a 2 pion state, pi plus, pi minus, and so on. And you have 4 pions and many more. So vector mesons. So everything which has quantum numbers of a photon can couple here. And if you calculate this, so this is the leading order hadronic vacuum polarization, as it's called. So this is giving this number, which is typically 7 or so, 10 to the minus 8. And the uncertainty here, so we have seen the total uncertainty was about 5. So this by itself gives an uncertainty in these units 4. So it's a large fraction of this uncertainty. And there are several of these calculations, but that's one of the ones which are typically quoted. And so there is some difference, of course, between the calculations, but within error bars they're still consistent. Now, how can we improve on this? So I will show you this a little bit later. So this hadronic vacuum polarization is basically means you need to know here the production of hadronic states from a photon. And so as you have seen, so I think Pete showed this, maybe it's still here. So you have space and time-like processes, and so one of the processes is a time-like production, so you have E plus, E minus annihilation goes in a time-like photon, and this allows to produce hadrons. So such experiments can be done at E plus, E minus colliders, and so I'll show you some of these developments. Now, besides this hadronic vacuum polarization, which in principle one can relate to data through this E plus, E minus into hadrons cross-section, there's a second process which is more difficult and which ultimately, when we we'll compare with the new Fermilab experiment, will become the dominant uncertainty. And that brings me to the topic of these lectures. This is so-called hadronic light-by-light scattering. And so this is the process where one photon is coupling to the muon line with 3 photons. So it's basically, it's a 4-point function, so involving 4 photons. So it's 2 photons going into 2 photons. And then you have all possible, so this block here shows all possible hadronic intermediate states. So the leading hadronic intermediate states, or the dominant ones, are the ones which correspond to the lightest degrees of freedom. And so you need hadronic systems which couple to 2 photons. And so typically a pi 0 is such a pseudoscalar meson, can couple to two photons, or eta, which are then heavier pseudoscalar methods. So an exchange of, for instance, a pi 0 will give you the leading contribution there. But there are many more. You can also have, of course, a 2 pi on pi plus pi minus there flowing. And the question is, how reliable can we calculate this contribution? Now, at present, so the numbers which are being used are typically 11, 10 to the minus 10, and the uncertainty here is also of the order 4. So here you see 4 relative to 700. That's a relatively precise estimate. Here, 4 relative to 11. It's not a very accurate calculation, so it's only 30% accurate. So definitely, so this is the one which is the toughest from the theory point of view. And in order to improve on this, of course, you can also improve by measuring photons, two photons fusion into such hadronic states. So that's the topic of this lecture. And technically, these are so-called meson transition form factors. So it's a transition, for instance, of a pion into, for instance, one real photon here. This is the external photon, which is real, and one virtual photon.
Can you remind us what's the current usual error bar? Give those numbers.
Here?
The current total.
Yes, so the current total theory error is 5. So it's basically the combination of these two.
And you say eventually you'll be done with my Taiwan, right? So
Yes, so I will just show you in a moment that this error, one is relatively confident one will knock it down by a factor 2, because it involves basically cross-section measurements, E plus, E minus, two hadrons, at the level of accuracy of 1%. So if you can measure hadronic cross-sections to typically 1%, which is feasible, okay, it's a challenge, but it's feasible, you can knock this down by a factor 2. Now here, in the second case, of course, one would like to knock it down by a factor 2, but you cannot relate it in a one-to-one way to an experimental observable. This is what makes it more difficult. So you need theory or eventually lattice QCD, but it's right now there are attempts, but it's a very tough quantity on the lattice. It's a 4-point function.
but the current error bar in the Photon Fusion is more than 1%, right?
Yes, but the 1% on a mu, yeah. But if you translate this to a cross-section, typically this corresponds with like 2% on cross-section, yes.
Mark, also in some of these other diagrams, you will not only need, for instance, time-like, where you can do measurements, but you also might need space-like.
Yes, yes. You need space and time-like. I will just show you this in a moment. So it's a combined, so you have different integration regions there. I'll come back to this point. So let's, maybe coming back to your point, let's quantify first this hadronic vacuum polarization. It's somewhat easier. So you can write this in a similar way I've shown you in the first lecture, using optical theorem and analyticity to a dispersion relation. So basically, this vertex function, a mu, it's a 3-point function, so a photon coupling to a muon. So you can relate it to the cross-section for E plus, E minus two hadrons. So it's basically, if you cut this diagram here in two, so this is a 2-point function which enters in this block. So the imaginary part of this 2-point function corresponds to the cross-sections of a time-like photon, so or E plus, E minus into hadrons. So and then you can do this integral, and this gives rise then to this formula. So we have an integral over energy basically, and the leading term, the first contribution, is when you produce two pions. So it starts from 4 and pi squared, and then it goes all the way to infinity. So you have this input is these hadronic cross-sections, which have to be taken from experiment. And then there's a well-known, just kinematical factor, which is a kernel function, which you have to multiply to get this a mu out. And just to give you an idea, this kernel, of course, is weighted. So the lower energies, so towards the lower energies, they have a much higher weight. And this is shown here on these pie charts. So basically what these pie charts show you is if you do this integration from 4 n pi squared up to 1 GeV here, you get already 3/4, 75% of the total contribution. If you do it then from 1 to 2 GeV, you get like another 20%, and then from 2 to 3 you get the blue region, and so on. So you see when you are at about here 8 or 9 GeV, and so once you reach these energies, you can basically replace this blob by a quark anti-quark blob, and then do the extrapolation to infinity using perturbative QCD. But you see the dominant contribution, at least up to 3 GeV, one cannot apply perturbation theory. So nearly 90% or so is in the regime where you cannot use the simple perturbative QCD expression. Now, some of these regions, of course, are known more accurately than others. So what is shown here is the same pie chart, but now for the uncertainty of this quantity. So this quantity, although it's large, we know it relatively accurate. So the uncertainty in the total number, so this actually is this 4. In this number 4, like 30% uncertainty comes from the region up to 1 GeV. And you see that more than 50% is coming from the region between 1 and 2 GeV. So if you want to improve and you want to make a real contribution, you need to improve, especially in this region here, 1 to 2 GeV, and then you can see the uncertainty coming from the higher regions. So it's really the lower energy region, let's say up to about 3 GeV, improving there is basically making the largest impact. So the energy range up to 3 GeV is essential. So let me just show you how these experiments are being done. So this is so I think everyone has seen this also. This is one of the indications for the number of quark flavors, and also the fact that quark have colors, so E plus E minus into hadrons. So as function of the energy, so there's a 1 over S tail, which is just E plus E minus perturbatively into quark anti-quark. And then on top of this tail, you have these vector mesons, so which are resonances, which are made up here of up, down, and strange quarks. And then once you hit like around 3 GeV, you get the J psi, so you get charmonium states. And then once you hit around 10 GeV, you get the bottomonium states, so the BB bar resonances. And you see these steps here each time, and this is when a new threshold opens. So this is here the charm threshold. So then the number of quark flavors increases by 1, and then you get an increase in these cross sections. So and it's basically, so this whole cross section here enters in this dispersion interval. So I was saying you need especially the energy range up to about 3 GeV. So it's in this range one needs to improve the data mostly. And so this is being done. It's a program which is done in quite some detail. And the main, so in Babar and Bell, E plus E minus facilities, they have contributed. They are somewhat higher in energy. So the main facility right now, which has the highest luminosity, which can contribute in this range, is BESS 3 in Beijing. And so this has a center of mass energy here, roughly, so about 4 point something. And now in order to access this whole range, so the process which is typically being used is the so-called initial state radiation process. So you have an E plus E minus annihilation, where you emit a photon which can be hard, and this photon is detected, and through such emission, so you lower the energy here of this virtual photon. So when this photon is soft, when this is 0, you basically access here this energy, and by radiating more and more of this photon, by detecting the scattered particle, you can access the range below this red line. So basically you can access here this whole range below 4 GeV. So this initial state radiation measurements allows to access the mass range, which is really relevant in this uncertainty for the hadronic vacuum polarization. So there's a whole ongoing experimental program, and actually there already first